where everything worked before. So, hello everyone, thank you for the introduction. My name is David Kozak, and as was mentioned in this presentation, I'm going to talk about comparing rapid type analysis with points to analysis in GraalVM Native Image, which is a joint work with Vojin Jovanovic, Codrut Stancu, Wimmer, and Tomáš Vojnar. In our paper, we focused on the problem of call graph construction for ahead-of-time compilers, which, among other use cases, is used to detect program elements that may be used on at least one path during the execution of the program and therefore have to be compiled and included in the binary. We call such elements reachable. The key difficulty when constructing call graphs are virtual methods, because for each virtual method, it is necessary to detect all possible callees in a way that is sound, meaning no real callee is missed, but at the same time, a reasonable amount of precision has to be maintained, because otherwise unnecessary methods are included in the binary. In this example, we could, for example, prune the method M in the class C based on the knowledge that it hasn't been instantiated in the application. In particular, we based our, or rather we work on GraalVM Native Image, which is an ahead-of-time compiler for Java that works under the closed-word assumption, meaning that all the code or all program elements that may be needed at runtime has to be available already during compile time, which poses restrictions on some dynamic features of the language, such as reflection or dynamic class loading, that has to be explicitly configured. A native image produces standalone binaries that contain the application along with all their dependencies and runtime components. Native image uses a combination of points to analysis, class initialization and build time, and heap snapshotting to produce self-contained and fastly starting binaries. The analysis in native image starts from a set of entry points that gradually extends, and each class that is marked as reachable can potentially be initialized at build time. And if it is initialized, then all the objects that are created during the execution of the initializer and that may be used later on during the execution of the binary have to be serialized and included during the snapshot phase. And the snapshot poses or reforms another input into the analysis, because types that have not been seen in the code but are part of the allocated object graphs have to be considered as instantiated as well when running the analysis. Unfortunately, using points to analysis in every build can be quite time-consuming. For instance, analyzing Spring Petclinic, which is a popular demo application of the Spring framework, can take up to 160 seconds. It might not sound like a lot for a static analysis method, but it is important to consider that this analysis is run during every build. So every time any developer wants to compile something using native image, this amount of time has to be invested into it. Therefore, we were looking for another alternative, cheaper analysis that would provide similar results with similar precision, but take less time. And the criteria we considered were, of course, scalability, then reasonable precision, because one must consider that we cannot simply include everything and mark everything as reachable, because it would increase the threshold, not the threshold, but the workload on the compilation phase afterwards. So any savings in the analysis could be outweighed by a more expensive compilation afterwards. On top of that, the analysis method has to properly interact with all features of native image, such as heap snapshotting. And lastly, we were also aiming for a method that could be incremental, so that the results from previous compilation can be reused in the subsequent runs. There is a plethora of methods of call graph construction, ranging from simple ones, such as unique name analysis, which considers only the name of the method when determining the callees, or class hierarchy analysis, which also uses the subtyping rules or class hierarchy rules, or rapid type analysis, which combines the class hierarchy along with the information about which types have been instantiated. And lastly, control flow analysis, which is very similar to what we have at the moment, and what we call points to analysis. After careful examination, we decided to implement a prototype using rapid type analysis, which we believe offers a good trade-off between precision and scalability. To give you an intuition into how rapid type analysis work, we will formalize it using three equations that compute two sets, R and I. R stands for reachable methods and I for instantiated types. The first rule is very straightforward. It simply says that the main method, or in fact any subset of entry points, is already included into R, and it starts the computation. The second rule is more complex, so we will go through it step by step. For each reachable virtual invoke in each reachable method, we take its type E, or rather we take the static type of the expression E on which the method is invoked, and we traverse all instantiated subtypes of the type. In this case, the declaring type is A, which is instantiated, and therefore we consider the method F as reachable. Its subtype B is not instantiated, so we will not consider its implementation of F. And its subtype C, again, is instantiated, and therefore we will consider it. The third rule is again quite straightforward. It simply says that in each reachable method, we have to mark each instantiated type as instantiated. Rapid type analysis has already been studied in the past, so let us now clearly distinguish what is the state of the art and what is the contribution of this paper. First of all, we designed an extension of rapid type analysis that is suited for the context of native image, meaning it can interact with heap snapshotting and it provides all the necessary information for the compilation phase afterwards. And therefore, it can work as a replacement or rather alternative mode for the points to analysis, which is used at the moment. Then we extended the basic algorithm to be parallel and incremental. The incrementality was achieved using concept of method summaries, which I will discuss more in the future. And lastly, we performed an experimental evaluation comparing rapid type analysis with points to analysis in the context of GraalVM Native Image. Let me now describe the core algorithm of RTA, including our extensions. It starts with a set of root methods that we mark reachable, and then for each reachable method, we parse it into its intermediate representation from which the summary can be extracted. Afterwards, the summary is processed and the state of the analysis is updated using a set of register methods that are called for each interesting element. Once a given method is made reachable, the decision is never reverted, which means that eventually a fixed point has to be reached and the analysis terminates. The core idea is now presented in pseudocode or the slide. I would like to draw your attention to the lines 4 and 5, because each register method actually starts with an atomic check that succeeds only on the first time, which ensures that even if multiple threads try to perform the same operation, only one of them succeeds, and it ensures that there is no reduced work. And on the slide 5, we can see that the actual work, or rather any bigger piece of work, is not done immediately, but rather scheduled as a separate task, which ensures that the analysis essentially works as a very parallel application that runs in a thread pool. Let me now proceed to the summaries. These summaries are rather straightforward. They consider the following information, from which I would like to highlight, for example, directly invoked method, virtually invoked methods, and instantiated types. And they can be easily extracted by a linear pass over the intermediate representation. Let me now proceed to the more tricky part of RTA, which is resolving virtual methods. First of all, the method itself is registered as invoked on its declaring type. The reason for that will be explained on the next slide. And then the actual subtyping, or rather all the instantiated subtypes are processed, and the method M is resolved on them using the resolve method actually performs virtual method dispatch based on the specification of Java. The other side of coin is registering new type as instantiated. Again, all the methods I mentioned start with the atomic check, which prevent from the reduced work. Then the type hierarchy is traversed upwards, and the type T is registered as instantiated in all its supertypes. Then the supertypes hierarchy is traversed again, but this time we are looking for all methods that are registered as virtually invoked in all the supertypes. But now please take attention to the line 7, because the resolution always starts from the type T, not from the supertype. So coming to the example on the right, suppose that type C has been marked as instantiated, and it already has method F registered as virtually invoked. We will therefore perform the resolution of the method f on the type C, which will result in f, and we will mark it, we register it for further processing. Then we traverse the hierarchy upwards. In this case, we are looking both for instantiated and non-instantiated types. So we are truly traversing all supertypes of the type. And suppose type B has method G registered as virtually invoked. We will again perform the resolution via the type C, which will give us the implementation in B. So we will register it as invoked. Then we go to the supertype A. And here it gets a little bit more interesting, because when we resolve its method f using the type C, of course we will get the one coming from the type C. And therefore we will not mark the one coming from the type A, which would be imprecise, unnecessary in this case, because there is no way the method f on type A can be instantiated in this case. Let us now run the analysis on a simple example. Suppose we start from the method main, which instantiates type hello and A, virtually calls method foo, and directly calls method lock. When we see the direct invoke of method lock, we can immediately register as invoked, because it is direct, of course. And when processing the virtual invoke foo, we have to consider all instantiated subtypes of the type hello, which in this case is only hello itself. Therefore, we resolve the method into hello.foo. When processing method lock, we only mark type B as instantiated, and then we proceed to the method foo, which accepts an interface type I as a parameter. And in this case, we have to consider all instantiated subtypes of the interface I, which in this case is both A and B. And therefore, we end up marking both A.bar and B.bar as possibly invoked and have to process them as well, which is a slight imprecision compared to points to analysis, which would determine the callees more precisely in this case. But at the same time, it would also need to create more complex internal representation to actually perform the analysis compared to a few simple summaries. Let me now proceed to the incremental part. The summaries contain mainly classes, methods, and fields, which are not so difficult to serialize, because for classes, we can simply use the fully qualified name. For methods, we can use a combination of the class name, method name, and signature. And for fields, we can use, again, class and name. Unfortunately, there are some constraints that have to be considered. First of all, not all method names are stable in Java, especially the generated classes that are created for lambdas, for example, are unstable. Their name changes from one compilation to another, which poses a problem. And lambdas are not the only example of this behavior. Then, at the moment, we only support so-called trivial embedded constants, meaning primitives or well-known types, such as Java-lang string, because we know that traversing, let's say, the transitive closure of all the objects starting from string will always give us the same set of instantiated types. So it's not necessary to consider them in the summary. Unfortunately, the incremental part has a significant problem when it comes to side effects during parsing, because unfortunately, parsing a method in GraalVM Native Image is not a pure function. It modifies a lot of state, and it can also even mark more methods as reachable, which is rather unfortunate, but at the same time, it is not an artifact of the analysis itself, but rather of the compilation environment, and might be eventually lifted during the effort of making the whole native image more deterministic. And the second issue is that summaries contain quite often non-trivial constants, meaning other types, and this restriction might possibly be lifted in the future. I have some ideas about that there was just not enough time to implement them. Let me now proceed to the experimental evaluation. We've performed experiments using the standard suites Renaissance and DaCapo, and apart from that, we've also analyzed several microservice applications from the most popular Java frameworks, Micronaut, Petclinic, and Quarkus. And you can note, for example, that for Spring Petclinic, we've managed to reduce the analysis time by 64% and the total time by 35%. Of course, at the cost of increasing the binary slightly and making more methods reachable. Similarly, we've reduced the analysis time for most microservices But at the same time, if you take a look at the first line, simple hello world application, the analysis time and the total time increased. And the result for that is that for smaller applications, the imprecision of RTA and the extra work that has to be performed for those methods that are marked as reachable only for rapid type analysis actually outweighs the benefits of simpler analysis. Then we've also experimented with different number of cores to inspect the scalability of the analysis. And now I would like to draw your attention to the scenario with 1 or 4 threads for PTA and RTA, because in those scenarios, RTA performed even better, which suggests that it might be a good candidate in environments with restricted number of threads, such as GitHub Actions or some continuous integration pipelines. To conclude the presentation, we designed an extension of rapid type analysis for the context of GraalVM Native Image. We extended the proposed algorithm to be parallel and incremental, which we achieved using the concept of method summaries. We've performed extensive evaluation, and for example, for Spring Petclinic, we reduced the analysis time by 64%. And as the next step, we would like to work more on the incremental part and also on a combination of points to analysis with rapid type analysis, which should possibly outperform both alone. That's all from my side. Thank you for your attention.
Do we have questions? So while you warm up, maybe the obvious question, how would a combination of the two look like?
Well, we haven't really published it yet, so I'm not sure how much I can talk about it. But let's say that in certain parts, when the amount of type in points to analysis exceeds a certain threshold, it doesn't really make that much sense to track it more precisely. I would stop at that because we are actually actively writing another paper where we describe this.
All right. Any other questions for David?
I'll make the other obvious question, which is, what's the work on making this incremental?
Can you repeat, please?
So one of the next steps would be incremental support.
Well, as I mentioned, there are two issues with incrementality. First of all, the side effects, which is rather a lot of engineering work. And the second part would be actually to include non-trivial constants or non-trivial embedded constants into the summaries, which could be possibly done by either traversing the subgraphs of those constants and simply including all the instantiated types in those objects into the summary itself, or alternatively, but that would require more engineering work, to actually track the decisions when it comes to inlining the decisions when it comes to inlining field accesses, and kind of determine where this constant came from. So instead of including the subgraph into the summary, you could say that this summary contains a constant that should be available from this static field in a given class after its initialization. And you can then replay the same thing in the next compilation.
Thank you.
All right. Let's thank David one more time.